So in this section, we're going to build up results from our graphing motion activity in order to look at how we can analyze the motion of an object from the object's position and velocity graphs. If you recall from our in-class activity, we use motion sensors in order to track the position and velocity of people in our lab groups in order to analyze and determine the conditions for an object's motion in terms of position and velocity graphs. Hence, this will be our topic for 1.2. So, interpreting position versus time graphs, okay? On position versus time graph, the position is represented on the y-axis while our time is represented on the x-axis. So a left motion corresponds to heading down on the position axis, while a rightward motion corresponds to our curve heading upwards on the position axis. So right here, for this example, for this position versus time graph, this would be an object that's strictly heading to the right, as we see that our position is heading upwards as time moves on. We go from 0 to 50 meters. If we were heading to the left, that would correspond to a negative displacement. So we would be, for example, for a leftward graph, we would be going from 50 to 0 meters as time goes on, and hence our graph would be heading downwards. Okay? The slope of a position versus time graph represents our velocity at some time t. The idea being is that if we take the slope of this graph right here, we're going to have our change in position divided by our change in time. But our change in position is our displacement, so we can see right here that this is in fact the equation for velocity. Okay, so as a result, the slope of a position versus time graph is the velocity at that specific time of interest. So for example, for the object of position versus time graph above, let's say we're trying to find our velocity at t equals 3 seconds. So what we would do is we would use the point t equals 3, x equals 30, and any other point on the line, your choice, you'll get the same answer, to determine your velocity at 3 seconds. So our velocity is change in position divided by time. So we're going to get 30 minus 10 divided by 3 minus 1. Here I'm using 1 second, 10 meters as my second point, which gives me that my average velocity over this time interval is 10 meters per second. So the slope of your position versus time graph can be used to interpret the velocity of your object over a certain interval or at a specific time. And we just covered this specific example right here, so there's no need to go back over it. So slope analysis of a position versus time graph. We can use our slope in order to determine when an object's speeding up, slowing down, or vice versa, okay? So the direction or arrow of the slope of the position versus time graph indicates the direction of motion. So we can see right here that our arrow is pointing upwards on our slope that we draw each point on our curve, indicating our object is heading towards the right. The steepness of the slope indicates the speed of our object. So we can see that our object right here is speeding up because we can see that our slope at each point on our curve is getting steeper and steeper and steeper. Again, the idea being is that steepness is like speed. It's simply a number. It does not consider direction. So steepness is a good indicator for speed, whereas the arrow is a great indicator for the direction our object is heading. So if the object speeds up, as we stated, the slope will become steeper. Again, as we stated, right here we can see that our slope at each point on our position versus time graph gets steeper and steeper and steeper. Now, if an object slows down, what we're going to see is that the slope at each point on our position versus time graph becomes less and less steep. It gradually becomes less and less steep. Okay, that indicates that we're traveling less distance, a less amount of distance in a given amount of time. So our object becomes less, or our slope becomes less steep when we slow down. So now, if an object changes direction, that indicates that we're going to be changing from, say, heading to the right or left, or heading from the left to right, which means that our velocity is going to change signs. AKA, if we head from the left to the right, we're going to change from a negative velocity to a positive velocity. So what we look for when an object changes direction on a position versus time graph is that the slope will change direction and briefly be 0. So we can see right here that our slope right here is negative, indicating a negative velocity because it points downward. We see that right here we have a horizontal tangent line, and then afterwards we can see that our object is now heading towards the right because our slope is heading upwards. In more layman's terms, we can see that our position is decreasing right here, so we're heading towards the left, and then after this time right here we can see our position begins to increase, indicating we're changing direction, heading towards the right. Hence, this is how we can use slope to analyze a position versus time graph. So now we look at interpreting a velocity versus time graph. Please be careful. Please be sure to be able to distinguish between a velocity versus time graph and a position versus time graph. Make sure you read the labels. Do you have velocity on the vertical axis or position on the vertical axis? Okay? So with a velocity versus time graph, when an object is heading in the right direction, the velocity will be positive on the velocity versus time graph. The idea being is that our velocity is now on the y-axis. So a positive velocity on the y-axis corresponds to our object heading towards the right, since positive velocity is associated with a rightward motion. When an object is heading in the left direction, the velocity will be negative on the velocity versus time graph. Again, the negative on our velocity versus time graph indicates a negative velocity, and negative velocities are associated with heading towards the left. And then a change in direction occurs when the velocity switches signs from positive velocity to negative velocity or vice versa, and the velocity versus time graph is briefly zero. Again, the idea being, like we saw the position versus time graph, is when we change direction, our object is going to go from one sign of our velocity, say positive, to another sign, negative, or vice versa from negative to positive. So if we look right here, from 0 to 1 seconds, our object is heading towards the right. Again, we don't look at what's happening with the graph right here. We look at the numbers on the y-axis. We can see our object heading towards right because the velocity is positive, indicating we're heading towards the right. And then at 1 second, we can see we're changing direction because we're going from a positive velocity from before 1 second to a negative velocity after 1 second. And again, this negative velocity indicates that we're going to be heading towards the left because, again, negative velocity is associated with leftward motion. So recall that with speed, we do not consider direction. So for this part, in terms of interpreting speeding up and slowing down, it is useful to think of all numbers on the velocity axis as positive, okay? So for speeding up versus slowing down, we consider this area to be positive right here for the time being. So the idea is that if we're speeding up, that means we're going to be heading away from the 0 meters per second. Because if our graph heads towards the 0 meters per second, that means we're going to be slowing down as we're reaching a speed of 0 meters per second. So when we're speeding up, our velocity versus time graph is going to move away from 0 meters per second on the vertical axis since the speed is growing. So for example, right here, we would be speeding up from 1 to 2 seconds. Even though our velocity is negative right here, remember that speed does not depend on direction. So we're looking at from 1 to 2 seconds right here, we see that our speed is moving away from 0 meters per second, indicating that our speed is growing from 1 to 2 seconds. So from 1 to 2 seconds, we're speeding up because we're moving away from 0 meters per second, and we're heading in the left direction since the velocity is negative. Likewise, if an object is slowing down, the velocity graph will move towards 0 meters per second on the vertical axis since the speed is shrinking. So if we look right here, we're slowing down from 0 to 1 seconds. Our velocity is positive, but because we're moving closer to 0 meters per second, that means we're slowing down because our speed is approaching 0 meters per second. So we're slowing down from 0 to 1 seconds. A useful way to think about this is in terms of a speedometer. When you slow down, the dial in the speedometer moves towards 0 meters per second, and when you speed up, regardless of the direction you're moving, the speedometer moves away from 0 meters per second. So hence, if we move away from 0 meters per second, we're speeding up, whereas if we move towards 0 meters per second, we're slowing down. So now we can connect position versus time graphs with velocity versus time graphs. If we have a constant velocity, that means our slope is constant, okay, since slope of position versus time graph is velocity. So we're going to get just straight lines. If we're heading upwards, that means our position is increasing, so we're going to have a positive velocity. If we're heading downwards, that means we're going to have a negative velocity. So as a result, if we use A to indicate heading upwards, or A to indicate heading in a positive direction, and B to indicate heading in a negative direction, our subsequent velocity versus time graph will be a flat line because we have a constant velocity that's positive for A since we're moving at a constant positive velocity. So here's a corresponding velocity versus time graph for A in this situation. And then for B, if we're moving at a constant velocity in the negative direction, we're going to have a flat line that is in the negative region of our velocity axis because our velocity is constant and our velocity is negative, indicating we're heading towards the left. If we're speeding up, if we're heading in the positive direction speeding up, we're going to be heading upwards indicating an increase in position, and our slope is going to be getting steeper. Because we're speeding up, that means our velocity is also going to head away from the 0 meters per second. And because we're also heading the positive direction, our velocity will be positive as well. So we're going to have a positive velocity that's heading away from 0 meters per second to indicate speeding up. Now, if we're slowing down, if we're speeding up and heading in a negative direction, our graph will look like this. Our slope will get steeper, but we're heading in the negative direction. Okay. And then the subsequent velocity versus time graph for an object that's speeding up and heading in a negative direction is going to be moving away from 0 meters per second, indicating that we're speeding up, and the velocity will be negative, indicating that we're heading towards the left. So again, for speeding up in a negative direction, our velocity will be negative, indicating we're moving in a negative direction, and we'll be moving away from the 0 meters per second mark on our velocity versus time graph to indicate that we're speeding up. And for slowing down, we have the same type of graphs, except our slope gets less steep for A, indicating we're slowing down. And on the subsequent velocity versus time graph, that means that our object's going to be heading towards 0 meters per second as we're slowing down. So we're going to have a positive velocity, but we're going to be heading towards 0 meters per second, indicating we're slowing down. And for B, if our position is decreasing, we're heading towards the left. Our slope is going to get less steep, but it's going to be negative, indicating we're heading toward the left and we're slowing down. On the subsequent velocity versus time graph, that means that we're going to be heading towards the left, so our velocity will be negative on the velocity versus time axis. And because we're slowing down, that means we're going to head towards the time axis, meaning we're heading towards the 0 meters per second mark on the time axis. Again, this is a lot of information to process. We're going to spend a good amount of time with this in class over the next couple of days. But make sure that you have these graphs down right here so that we're ready to go with practice, okay? So producing a velocity versus time graph from position versus time graph. The main idea to produce a velocity versus time graph from position versus time graph is that we're going to calculate the slope over each time interval, since that will give us the velocity over that time interval, and then we're going to graph the subsequent slope on the velocity versus time graph, okay? So for example, from 0 to 5 seconds, we have a constant velocity, and we calculate the slope as 1.25 meters per second. At 5 seconds, our object changes direction as we're going from a positive velocity, aka our slope is positive, to a negative velocity. Our slope is negative for our position versus time graph. From 5 to 10 seconds, we can see that our velocity is negative because our slope of our position versus time graph is negative. And when we calculate that slope, we're going to get negative 1.6 meters per second. And lastly, from 10 to 15 seconds, our position doesn't change at all, which means we're at rest and our velocity is 0 meters per second. So the next thing that we're going to do is we're going to take these values and we're going to plot them on our velocity versus time graph. So what that means is from 0 to 5 seconds, our velocity is 1.25 meters per second. So we draw a flat line there, indicating that constant velocity. From 5 to 10 seconds, we change directions. We see our velocity goes from positive to negative. And from 5 to 10 seconds, we see that our velocity is negative 1.6 meters per second. So we graph a flat line at negative 1.6 meters per second. And then from 10 to 15 seconds, we have a flat line at 0 meters per second because our object has a velocity of 0 meters per second from 10 to 15 seconds. And thus is the process that we use to produce a velocity versus time graph from a position versus time graph. And lastly, now we look at one last topic here. How to produce a position versus time graph from a velocity versus time graph, meaning we're going in reverse. Again, this is a lot of material, so we will spend a lot of time with this, so do not feel weighed down if you feel yourself struggling a little bit. We will spend a good amount of time with this in class. So first thing we can recognize, if we want to go from a velocity versus time graph to position versus time graph, is that if we rewrite the velocity equation, we can solve for our change in position. So our change in position, by multiplying both sides by delta t, is going to be equal to velocity times change in time. But if we look at the velocity, a velocity versus time graph, we can think of velocity as the height of a rectangle, and delta t as the width of a rectangle on a velocity versus time graph. So the area of a velocity versus time graph is going to be velocity times our time interval. Again, our height is velocity and our change in time is delta t. So as a result, we come to the conclusion, seeing that we have the same equation for area and the same equation for displacement, that the displacement of a velocity versus time graph over a certain interval is simply the area between the curve and the time axis. So we want to calculate displacement for velocity versus time graph over a certain time interval. We simply calculate the area between the velocity versus time graph and the time axis. If we want to calculate the final position, then we take the displacement we calculate from this area and add it onto our initial position. The idea being is that our final position is equal to our initial position plus our change in position. So let's see what this looks like in practice. A GPS tracks the motion of a car as follows on the velocity graph at right. If the car starts at initial position of 12 meters, what is the position of the car at 15 seconds? So what we can do right here is break it up into time intervals and calculate our displacement over each time interval. So we see that our displacement is going to be a triangle from 0 to 5 seconds, another triangle from 5 to 10 seconds, and a rectangle from 10 to 15 seconds. So the first triangle is going to have an area of 25 meters. We have 1/2 times 5 seconds, our width of the triangle times our height, 10 meters per second. And then for a second triangle, we have the same area, except because the velocity is negative, it's going to be negative 10 meters per second. We're going to have a negative area. And then over the last rectangle, we're going to have a width of 5 seconds, and then a height of negative 10 meters per second. So our rectangle is going to have an area of negative 50 meters. The two triangle areas will cancel out, leaving us with a total displacement of negative 50 meters, meaning our object is headed to the left over this time interval. So now if we want to find our final position, we're going to take this negative 50 meters and add it onto our initial position. So 12 meters plus negative 50 meters is going to give us a displacement of a final position of negative 38 meters. And this has been a lot, but this is perhaps the longest video you'll see all year, perhaps the longest lesson you'll see all year. And we will spend a good amount of time with position versus time graphs in class, as they do make up a huge chunk of exam and do have a lot of content involved with them.